Hello, everyone, and welcome to another wonderful, great day of physical chemistry. So last time we were talking about three-dimensional rotations of a diatomic molecule. However, it turns out that not every molecule is gonna be diatomic. It turns out that a lot of our molecules are going to be a lot more complex. So due to this large, and one of the first things is that, of course, they're going to be larger in size. But also, one of the bigger things is they're not going to be quite as symmetric. And this has some very important consequences on those moments of inertia. Because remember, the moments of inertia are all talking about how the system moves around the center of mass, which again is the important part about rotations. Well, as you look at a real molecule, like this trichloro ethane, what you're going to notice is that it's going to have a very different rotation about the z-axis than it does about the x-axis or the y-axis. Each one of those are going to have a very significant kind of rotation. And we're going to need to acknowledge that some molecules are going to have very different moments of inertia and thus angular momenta, depending on the direction. So what we're going to need to do, and we're going to predominantly focus on today, is how we're going to essentially account for these different moments of inertia. So one of the first things we can do is try and figure out what we're going to use these moments of inertia for, why I should care. And that really comes when we go back to our energy equations. Because remember, we establish a set of energy equations that exist for each axis. So the energy of rotation about the y, x, y, or z axis. Now, I do want to emphasize this is about that axis, not in that direction. But the energy of rotation about the z-axis is going to be dependent on the moment of inertia in the z-axis and the angular momenta, or the angular velocity in that axis. So as a result, we're going to want to calculate each of our three major axes independently. And we can do this by utilizing our good old equation of the moment of inertia can actually be given by the sum of the masses of each of the atoms and the distance from the center of the axis, which can be thought of again as the center of rotation. Once we have these angular momenta, we can go ahead and combine them with our angular once we have these moments of inertia, we can combine them with our angular velocities to get an overall energy for the system. So we can think about our energy as going to be the sum of the angular momenta, which again are going to be based on moments of inertia and angular velocity over the moment of inertia for each direction added up. So we'll deal more with these parts of the expression next time. Today we're going to be exclusively focusing in on this moment of inertia. And one of the reasons why is that this actually is going to involve some kind of tricky geometric math and physics. So if I've a good place to start is going to be with a linear molecule, because who doesn't love a good linear molecule? This way I only have to really worry about one axis. In truth, what I'm going to have is one axis where the moment of inertia is 0. So you can imagine rotation about the bond. Every atom exists on the axis, so its moment of inertia is going to be 0. And because its moment of inertia is going to be 0, so will its energy. This means I only have two moments of inertia I actually care about. You can think of one as bisecting the bond this way, and one is bisecting the bond coming in and out of the board. Now, because of the nature of this bisection, we're going to have two identical moments of inertia in those two directions. So we tend to just shorthand this as I. So we're only going to give it the one moment of inertia. And this is exactly the one we've talked about before. So what we again will come into play is what's going to matter is the distance of each of these atoms from the center of mass, and then again corrected for how far it is from that center of mass. Now, trying to find the exact center of mass for a diatomic molecule, honestly, not the easiest thing. So what we do is we replace that expression with a well-known expression for the moment of inertia for a two-body system. And yes, this is our good old friend. This is the reduced mass, where it's essentially the two masses multiplied, divided by their sum, times the length of the overall bond. So again, diatomic molecule, we have only two moments of inertia, both of which are equal, and both of which are given by the reduced mass times the bond length squared. So we already know how to solve this system. Woohoo! Always love a good pre-solved system. However, for triatomic molecules, we have to quickly divide this into two key groups. One is going to be a triatomic linear molecule, where we have identical atoms on the outside. So think about something like carbon dioxide. And then the other one is going to be where we have two different molecules, or two different atoms on the ends of the molecule. Think about something like hydrogen cyanide. So the simpler one is going to be with two identical atoms on the end. And for this one, we get very lucky because the center of mass is that central atom. So all we need to do is calculate the moment of inertia by taking the mass of each of our atoms times the distance from the center of mass, which just turns out to be the mass of the outside atoms times the distance squared for both of them. So they're identical. So it just becomes twice the mass of the outside atom times the bond length. So that one's actually not too bad. Now, when the bond lengths are, when the atoms are different, now we have a little issue because my masses are going to be different and my bond lengths are different, which means that what ends up happening is my center of mass ends up shifting. And we can essentially account for that by adding an extra correction term here on the end. So what we say is that, okay, if my if atom A is heavier than atom B, then what we tend to find is we'll have a extra correction factor that accounts for the center mass shifting towards that mass A, which is, by the way, going to always reduce the moment of inertia, because essentially rotating about the center of mass will always have a lower moment of inertia than rotating about any other point. And so we'll then have a value where we just subtract out pretty much the mass and the bond length of the lighter atom from the heavier atom, square that value, make sure that everything stays positive, and then divide by the total mass. And if you double check, you'll also find that this has the correct units. But again, what this is going to do is it's going to help correct our moment of inertia by moving the center of mass to the correct location. And again, this is a much easier way than trying to solve it by hand, at which point you first need to figure out where the center of mass is, and it's a big mess. However, it also turns out that not all molecules are going to be linear. So the next most complicated system is called the spherical system. So these are spherical rotors, and one of the ways you can think about it is that these things are going to be very symmetric, as demonstrated by the center of mass will actually be the center molecule. So we have two classic cases of a spherical rotor, and those are first a tetrahedron. So if I have a symmetric tetrahedron system, this is something like methane or tetrachloromethane. So nice, simple system. Carbon loves to do this. What we find is that we're going to have a moment of inertia equal in every direction. The influence of bond angles do kind of come into play, but they also tend to cancel out a lot. And as a result, what we can do is, using some simple trigonometry, show that the moment of inertia can be given by using the mass of the exterior atoms and times the square of the bond length. And then we essentially account for having multiple atoms out here, along with the fact of that bond angles by adding in a factor of 8/3. So this one's actually nice because while we do now have 3 different moments of inertia, again, they're all going to be equivalent no matter which way you look at the system. And they're only dependent on a single mass. Interestingly, it actually gets a little bit easier if you have a symmetric octahedral system. So this is very common in metals. And one of the ways we can almost do this one by inspection. You can imagine rotation here about the z-axis, at which point I have 4 atoms away from the z-axis, each one with a mass of A and a bond length of R. So since I got 4 of them, the moment of inertia is just 4 times the mass of the exterior atom times the bond distance. So fairly nice, simple expression. Things get a lot more complicated when we go to a symmetric motor. So a symmetric rotor is essentially going to be a molecule where I took a spherical rotor and then I messed with one of the axes. So it's going to have 2 identical moments of inertia. So say in this case, in the x and y direction, and then another axis that is very different. In both of these cases, the z direction. And so what we're going to need to do is treat these 2 different moments of inertia separately. So if I have, say, this trigonal pyramidal system, its parallel moment of inertia, which is going to be the moment of inertia that is by itself, so the one that stands out, in this case, the one that goes along the z direction. This one can essentially be given, again, by the mass and the bond length, and then we have to essentially account for the angle. So here, what I have to deal with is my rotation is slightly essentially shortened out because I'm not existing 1 full bond length away from the center of atom. It's just a little bit less. So we correct for this using 2 times 1 minus cosine theta, where theta is the bond angle. We can similarly apply some trigonometry to get the other 2 axes. So these are going to be the perpendicular moments of inertia. So you can think about these as the ones that cut through in the other direction. So for example, along this AB bond, and then directly 90 degrees to that. And they involve, well, let's be honest, a little bit trickier math. And one of the explanations for this and this high dependence on the cosine of the bond angle is that these are going to be kind of tumbling all over themselves. So in this case, we really are we become quite an uneven rotor. And as well as we have to acknowledge that the center of mass is not at atom B, it's going to be slightly below it. And this is also what's taken into account when we're bringing in the bond angle. However, we also have other examples of symmetric rotors. For example, you can imagine an octahedral complex with 2 transligands. This is one of the more simple modified octahedral cases. And again, this one almost is, again, easier by inspection. The parallel bond axis is going to be along these 2 odd atoms. So again, we're going to have the same moment of inertia we did with the spherical system. However, we do have these different perpendicular axes running down our AB bond. So at this point, what we now have is 2 atoms of A, and sorry, this should be mass of C, and 2 atoms of C sitting out here on the ends. Now, once we have all these moments of inertia, we can go ahead and use them to calculate all of our energy levels, all of our angular momenta. And it turns out that our rotational spectra will be a lot different for these symmetric rotors than we would expect from a simple linear or spherical. So next time, we're going to kind of start by digging in on the simple cases of linear and spherical rotational spectra. And then we'll go into symmetric rotor spectra. And it is worth noting that there are also going to be asymmetric rotors and a lot more types of symmetric rotors than the ones I presented here. But this kind of gives you a taste of what we're looking for. So next time, let's get into some microwave spectroscopy. Until then, take care.